Hello everyone. Today we're going to apply this idea of differentials a little more algebraically. And you'll see what I mean. I want to sort of show what we mean when we say that differentials are little bits, small differences in a variable, in an axis, so to speak. Let's work through this example and show you what I mean. We have y equals x squared. So we're going to try and find the derivative of this. So we want dy over dx, the derivative of y with respect to x. So I'm going to just rewrite this equation a little bit differently. Okay, so y equals x squared, but instead I'm going to now add a little bit of x to the input, that is dx. We're going to add a dx into our input, okay? We're going to nudge the input a little bit. So what does that mean? What does it mean to nudge? So say we have x over here. So this is x. This is x. So let's say we just nudge over here. We just go a little bit to the right, okay? This distance that we've just created right here is delta x, but we want this difference to go so small that these two lines are practically on top of each other, so to speak. They're so infinitesimally close, such that this difference is just going to zero. And when we say that, we just say it's a differential dx, right? This is a differential. And the idea is that if the difference can become so very small, you don't really have 2 points anymore. Rather, you just have 1 point. So when you connect a line to those points, you don't get a secant line that intersects 2 points. You get a tangent line that intersects 1 point, and that will tell us the rate of change of this function. So that's the idea here when I write this differential here. And conversely, this also results in a corresponding difference in the output, right? So that's going to be our rise. So dx is our run, and this is our rise. So dy. So we'll have to incorporate that as well, as so. Right? So a change in the x input a little bit will cause a little bit of change in the y input. That's all that I've said here. So let's continue on with this. So we're going to have dy plus y is equal to, this is in the form of a plus b all squared. So we're going to have the first variable squared plus 2 times ab, so that's going to be 2x dx, like so, plus b squared, which is dx, so dx squared, like so. Okay, so we're looking for the derivative dy over dx, but how do we go from all of this to that? Well, we can divide by dx, but it wouldn't really make sense to do so. If we do that, then we still have this y over here, and we still have this x squared, and this might cancel out, but this won't because it's squared. So what do? Well, I want you to understand this idea of smallness, okay? Because remember what a differential is. It's a little difference, right? But when you have something like 1 over 100, so a small number, right? This is just 0.01. I want you to go ahead and square this number. You can choose any small number, it doesn't have to be this. But when you square a small number, you're going to get, well, let's square this. It's going to be 1 squared all over 100 squared, which is 10,000. And this is equal to 0.0001. So the amount of zeros stay the same. Now notice that upon squaring a number that was, say, close to 0, we now have a number that's even closer to 0. It's much, much closer to 0. That is to say, it's a lot smaller, right? Let's say you're measuring something with a ruler, and maybe you're concerned with the amount of centimeters that it may come out to be, right? But you're not exactly concerned with the amount of millimeters it might be, right? So the only extent to which accuracy is required is to the second decimal place here, let's say. And you don't need any more than that. You would say that that extra few decimal places, those extra few digits, are negligible. It's too small to care about. It's not required for your purposes. In the same way, rather, a more extreme way, because this differential dx is much, much smaller than 0.01. Much, much smaller. So when you square that number, you get an even smaller number, a number that is another degree of smallness greater, let's say. It's another magnitude that we don't need. So we can actually just cross something like this out and say that it's negligible, right? Because this differential is being squared, and we originally started with differentials to, you can imagine, a first power there, right? That's the standard of smallness. That's the only degree of smallness that we need. Anything more than that is negligible. Just as when you're measuring, maybe you don't need the amount of millimeters, you just want how many centimeters it might be. So let's continue on with this dy. We can get rid of this y here by making a simple substitution. Because y is equal to x squared, we can actually just substitute in x squared, like so. X squared is equal to x squared plus 2x times dx, and then we crossed out the dx squared because it's pretty much 0. Now you'll see why I made this substitution, because we can just subtract x squared from both sides, like so. This cancels it out, and we're left with dy is equal to 2x dx, like so. We're looking for the derivative. We can simply just divide both sides by dx now, and we now have our derivative on the left side. Dx cancels out on the right side, like so, and we are left with dy all over dx is equal to 2x. That is our derivative. Okay, so that is to say that if you want the slope of a tangent line to some point on the curve of x squared, then you just need to plug in that particular x value into this function right here, 2x. And the value that you get is the slope of this line, of this tangent line, the m, the rise over run, right? So that is essentially what this gives you. Okay. Now, this was an interesting way to do a derivative. You might not have seen it before, but let's keep going with this, because we can actually derive something here, a pattern. Let's say we have something like y equals x. This is a little bit of a simple example than the last one. So let's add our little nudge. So we're going to do x plus dx, right? So we're going to start somewhere on the x-axis, and then we're just going to nudge a bit, okay, like so. And then this difference is dx, okay? And this corresponding difference causes a corresponding small difference in y. So we're going to have plus dy, like so, okay? There's no differentials being squared here, so we can skip that step of negligence, and we can sort of make our substitution here that you'll notice, like we did before. You can substitute y for x, and we'll have dy plus x equals x plus dx, like so. We can subtract x from both sides now, like so. We can get rid of them. And now all we're left with is dy is equal to dx. Notice what this means. If you nudge in the x direction by a little bit, the corresponding nudge, if you look on the right here, will be exactly the same in value. Okay? But remember, these 2 points, they're not 2 points exactly. Remember, graphically, they're supposed to go so very close to each other that it's practically 1 point, right? But what this is saying is that the difference in y is equal to the difference in x. And this makes sense because y and x are equal to each other. Whereas in the previous example, y is not equal to x, it's equal to x to the second power. So a small difference in x will result in a different difference in y. Okay. Remember, we're finding the derivative, so we can just divide by dx, like so. And we'll have dy all over dx is equal to 1, right? Because this cancels out to 1. Same on the top, same on the bottom. That's our derivative. Interesting. So our derivative is now a constant. So the tangent line, the slope of a tangent line to this curve x will be 1, no matter what. This makes sense, right? If you look at this point right here, well, any point rather, anywhere you want, the line that you draw, the tangent line specifically, will just overlap with your original function. And the slope of this line will always be the same. It's just going to be 1. This makes sense because y equals x. When you write y equals x, you assume that there's a 1 there, and this 1 is the slope, right? If you write in y equals mx plus b form, where b is just 0, because b represents the height of the function, right? This is the y equals mx plus b form, right? So the slope, m, what we're looking for, the derivative, is 1, and we can see that in the function, which is quite interesting. And this, writing it like this only works for the linear functions. We couldn't write the y equals mx plus b form for this because it's not a linear function. Okay. So let's try a slightly more complicated example. We're going to go to the third power now, and I'm going to do this a little more quickly just so I can prove a point. So we talked about deriving something here, and I think you might know what it is already, but if you don't, then stay tuned. I think you'll find this rather interesting. So let's say we have y equals x cubed. I won't be graphing this time, but we're going to be using the same method where we sort of go into our input and just change it a little by adding a little bit of x dx, right? You'll notice that this is in the form of a plus b all cubed, which is equal to all of that. And remember, don't forget that a change in your input results in a corresponding change in your y. So let's write this out, dy, and I'll make this substitution now where y is equal to x cubed. We're going to be canceling that out soon, so I'm just going to sub that in now. So we're going to have x cubed like so. We're going to have x cubed, if I'm going to expand this according to the formula, plus 3x squared dx plus 3x dx squared. notice that I'm not putting brackets around this dx like this, because this is ultimately just one thing. The d is not a variable. Please notice this. The d is not a variable. It is an operator, right? It's to just tell you something. Just as delta x is one thing, it's to tell you that this is a difference in x. The d in the differential tells you that this is a small difference in x. So we can keep going, and we just have b cubed, which is dx cubed. Again, we don't have to write the brackets. We can just write it like this. Okay, so now we'll have to come back to our idea of smallness, because now we have differentials being squared and cubed, right? Remember that any magnitude of smallness that you have extra, so to speak, will be negligible. We don't need it because it's too far out our, let's say, our required degree of smallness, right? So the difference in smallness that this differential gives is already so small. Anything smaller than that, which if you square a small number you get even smaller numbers, will just be negligible. It'll be too small to make a difference, right? So again, we can cross something like this out because that's cubed. That makes it even smaller. This is squared. It's another magnitude smaller, and it's being multiplied by 3x. So this whole term, like you can imagine this dx as a 0 because it's so close to 0 that we don't need it. So we can cross out this entire term like so. We won't cross out this term because this is to the power of 1, which is what we started with, if you like to imagine that 1 there. This is the degree of smallness that we want, the centimeters that we want to measure, if you will. We're not actually measuring in centimeters. That was just an example that I like to talk about. But if we continue on with this, right, you remember that if we subtract x cubed from both sides, we can get rid of that. And now we're just left with dy is equal to, so now we're just left with this term right here, 3x squared dx, like so. We can divide both sides by dx, like so. These dx's cancel out, and we're just left with dy all over dx, the derivative of y with respect to x, that's what it says in English, is equal to 3x squared. Interesting. So maybe you're already beginning to see a pattern here. I may have rushed this a bit, but you can keep applying the same pattern to x to the 4th, x to the 5th, and so on. But let's try and see this pattern here. When we have derivatives of variables to some constant powers, so x to the 1, x to the 2, x to the 3, and so on, we'll notice a pattern here. Okay, so this is really just x to the 1, right? And when we differentiate x to the 1, so d over dx of x over x to the 1 is just equal to x, or sorry, it's just equal to 1. But you can imagine there's an x there, but it's just to the power of 0, right? Because now we can sort of see the pattern here. Look at this. The constant 1 is now out here, and the power is 1 less than the original power. Let's look at x squared. We bring the 2 over to the front, like so, and the power is 1 less than the original power. 2 minus 1 is 1. If we have x cubed, we bring 3 out to the front, like so, and now we have 1 less of the power. 3 minus 1 is 2, like so. So what do you think this will be? Without doing all the math, which this would take a long while to do, we can just write this as, bring the power to the front, according to our pattern, 4x to 4 minus 1. So that's just going to be 3. So 4x cubed. And if you did the math, this would turn out to be correct. But we can write this pattern out as an equation, as something that you'll find to be very, very useful. And you probably already know it. It is indeed the power rule. So if you differentiate a function that is a variable to some constant power n, it is simply just equal to the variable multiplied by the constant n out front, like so. So we're going to have x, and then 1 minus, or sorry, the power minus 1 will be your new power. So this is essentially the pattern that we have here. And this works. If we have something like the derivative of, if we need to find the derivative of x to the 77, you're not going to expand all that. That you could, but it would take you hours, if not years. You wouldn't want to do that. So what you could do is use this pattern. Bring the 7 out front, or the 77, like so, and keep the variable, and then multiply or raise the variable to the power of 77 minus 1. This number, power minus 1. So 77 minus 1 is 76. So that's your derivative. This is the power rule, which we have just sort of derived here by looking at this pattern here. By using first principles, we could understand a very important idea of change and differentiation, and how differentials are used in an algebraic way. And so we can use this power rule in further applications when you have powers that are so big that it would just be too tedious to work out algebraically. You can just simply use the power rule, and this will be very, very useful going forward. Thank you for watching, as always, and I'll see you back in the next video.